Hello, everyone. Welcome to our tech briefing today. So we have got me and Javi, and we have two guests today from Mozilla research team, Nathan Egge and Michael Bebenita. So they have been Mozillian for a long time ago, and they are here today to share or to introduce the AVA1 and the open video codecs project. So they will start the presentation, and after that we will get a lot of some questions from the tech speakers channel and from the Etherpad, and maybe we will have this little discussion after all. So Nathan, whenever you are ready, you can just start.
Okay, great. Yeah, thank you. So yeah, I'll be talking today about the AV1 video codec. So at Mozilla, we ship the Firefox web browser, but we also do a bunch of work in open standards where we go to different standards bodies and advocate for royalty-free open standards that are accessible to all. And that includes some of the work that we're doing on codecs, which falls under this Mozilla Research or Emerging Technologies group. So to kind of frame the problem, currently in North America, about 70% of all internet traffic is video or audio streams. That was taken from a study in around 2015. There's been a more recent study that came out last year from Cisco that estimates that that amount will probably go up to 82% or higher by 2021. Interestingly, they actually project that all internet traffic will go up on an average about 25 or 30% in that time period. So we're not talking about a small gain of a few percent here. We're talking about a massive amount of additional content in video. And that's mostly due to the fact that we're expecting to see people pick up 4K, 8K streams, 10-bit video or high definition video. So to give you kind of a history of Mozilla and royalty-free codecs, there's a long history there. And in fact, many of the people working at Mozilla in this space were part of the Ziff.org Foundation and have been doing this work since the late 90s. So in terms of our work with royalty-free codecs, there was the Opus audio codec, which work began in 2007, based on a high definition, or excuse me, the original idea was to have this high quality, low latency music codec. Originally, the use case we were looking at was doing distributed performance, where you had people in different geographic locations who wanted to play musical instruments live and have a distributed concert. So this video codec was developed there. We took it to the IETF with the idea of standardizing it, and at the same time, sort of Skype came to the IETF with this high quality speech codec they had, and it was sort of a low bandwidth speech only codec. And the IETF asked us, couldn't you guys figure out how to join these together and make one standard? And so that's how Opus was born, through this collaboration. It was published at the IETF, and if you if you look at the broad set of use cases, it can go from very low bandwidth, low quality voice all the way up to like stereo, high quality music. And in fact, for all use cases out there today, if you were starting a new project, you'd want to begin with Opus just because it's so broad and covers everything. So this is a great success story. At the end of that process, someone from the IETF said, well, that's nice you did this for audio, but it's impossible to do the same thing for video. The IP landscape is too complicated. And so we decided, okay, great. Well, let's take a look at the video space. And Mozilla created the DALL project to look at doing sort of something similar that we did with Opus for video. And here the idea was to sort of be royalty-free by design. So we took all the kind of common areas that are done for video compression and decided to do something radically different. So we had a bunch of sort of interesting experimental ideas that no one had ever tried before. And part of the research challenge there was making them work. We brought this to the IETF and we were able to form this NetVC working group. And at the same time, kind of similar story, Cisco had this Thor video codec, which was great for video conferencing, whereas Dala was sort of targeting for video on demand and streaming. And so we were going to kind of take the best of these two products. A little bit later in the year, the licensing terms were coming out for HEVC, and a lot of people were recognizing that this royalty-free video was a big problem. And so the Alliance for Open Media was formed in the fall of 2015. And our idea was to contribute $1 to that. So let's talk about the Alliance for Open Media. It had there's a couple goals for the Alliance. The first is to produce this video for a broad set of use cases. So the idea is to handle both video on demand and streaming, as well as video conferencing, screen sharing, um, video game streaming, which is different from screen sharing, and broadcast, which has a different set of constraints. The idea was to be open source and royalty free, and with wide adoption and broadly supported. But most important, we were targeting 30% better compression than the current generation of video codecs. And by this, we mean at the time VP9 and HEVC. All right, so who's in the Alliance? So when we first formed the Alliance in the fall of 2015, we had 8 founding members. Now there are a lot more. These members include hardware companies, software companies, content producers, companies that stream content, companies that do real-time conferencing, and browser vendors. And what's really important here is that Apple joined the Alliance in late December, early January, and that meant that now all 4 browser vendors are part of the Alliance and are committed to shipping AV1 in some form shortly after the Bitstream is finalized. This is great for open web and open standards. It will certainly, if you've been part of any of the standardization process for other sort of video related things on the internet, you'll know that there's been a lot of issue around getting consensus for, what's the mandatory to implement codec for, say, WebRTC. Like, we don't have one, we have 2 because people couldn't come to an agreement. So now that we have all the browser vendors on board here, we think that'll help drive the use of this high quality video compression technology and create new products. So let me give you sort of a high level overview of what codecs look like. So I can say with some confidence that most video codecs, if you were to look at them, they've got these sort of broad categories, right? You'll have this prediction stage. You'll take the output of prediction. You'll go through this transform stage. And you'll take the output of the transforms and you'll do some quantization. And then you'll take the data from quantization and you'll do some kind of entropy coding. And they all kind of have this flow. When you talk about like where compression comes from in video codecs, it comes from mainly 2 places. The first place is prediction. So if you were to compare like 2 adjacent frames, the second frame, if you're in this video stream, like the next frame is like going to look very similar to the previous frame. And so the idea is if we use that as a predictor, we can remove a lot of redundant information. And then the other place we get sort of high compression gain is through quantization. When we do this transform step, we kind of compact all the energy into these smaller coefficients or these lower frequency coefficients, and all the high frequency ones we can just set to 0. And maybe you'll miss some like nice detail in the image, but you'll generally see the whole image. And this is really clear on, say, video streams where it suddenly like cuts to a very blocky image. That's where all the high frequencies have been lost. So one of the things you can do to compensate for the artifacts that are introduced through this quantization step is to add a loop filter. And the idea here is that after the decoder has reconstructed this frame and it has all these artifacts in it, it can run this post-processing filter that kind of smooths out those artifacts. When that filter is done, when that filter is applied to the frame before it's used again for prediction, we call that an in-loop filter, and that becomes like a normative part of the spec. If it were done afterward just for displaying, it wouldn't be part of the normative part of the spec, and you wouldn't get as good compression gains, right? Like having it as part of this in-loop filter, it's more expensive, but it means that you get better gains. So that's generally what all kind of video compression codecs look like. These are the coding tools that are in AV1 to kind of give you more detail. So I won't go into all of these. If you were to compare AV1 to, say, VP9 or HEVC, you would look and say that, okay, well, you've taken sort of the standard tools that we have and you've made them better, right? So instead of having 8x8 or 16x16 blocks, we have 128 by 128 blocks. So we have a bigger area with which we can predict over. That's going to be great for 4K and 8K content. We've got rectangular blocks. And so if you think of, an image or a scene that has sort of detail that's along sort of vertical and short edges, like having these rectangular blocks means it compresses better. We've got more transforms. So we now have up to 16 different transform types. And again, that helps us just match content better. And then for the sort of newer innovative things, like we've got a larger set of intra-prediction modes. We've got something called Chroma from Luma, which is a technology that came from Dala. We've got intra-block copy, a bunch of things that are kind of innovative. And we've got a bunch of new loop filtering techniques, like I mentioned earlier, that are somewhat innovative. So if you take this this list here, the ones that are in black are the ones that were part of the crazy things that we tried for Dala and were able to port over to AV1. And I'm going to talk about them a little bit more later. But first, let's look at how these fit into diagram I showed before. So of these 5 blocks that kind of make up video coding, we actually had technology from DALL-E that we tried to contribute to AV1 in all of them. So we had a Chroma from Luma intro predictor for prediction, which is a special intro mode. We had this DALL-E transforms, which were sort of a high efficiency transform. We had this PVQ quantization, and if you've been following any of the DALL-E development, that's one of the things that's sort of unique to DALL-E and got a lot of accolades when we published a bunch of, we went to conferences and got some academic review on it. We have a multi-symbol entropy coding coder, which is different from other video codecs, but it's actually very similar to the one that we used in Opus to big success. So that's actually, I'll talk about that more, give you more details there, but that's something that we thought would be a big win for video. And then we have this constrained directional enhancement filter, which is a port of the filter that was used in DALL-E. So I'll give a little bit more detail about these different techniques. Oh, just a point. So the DALL-E TX and the PVQ, even though we put those into AV1 and they showed great promise, ultimately this was a decision by consensus, right? We had 33 different member companies coming to agreement, and so those didn't make it into the final AV1 spec, but they did show promise, and maybe will show up again at some other future codec. All right, so I'm just going to go through some of these things to give you a flavor for why we contributed these technologies and why you should be excited that they're in AV1 and how they're going to improve it. So this multi-symbol entropy coder is a way to take an alphabet of symbols, typically when you do your entropy coding, you break things into a bunch of binary symbols and you code these ones and zeros with some probability. What we've done is we've kind of grouped them together to form alphabets. Instead of alphabets of 2 symbols, or alphabets of up to 16 symbols. And the reason this is an improvement in AV1 is that we can more accurately predict those symbols, and we also get a benefit from being able to clock more information through our entropy coder at lower frequencies. So if you're decoding something, if you're decoding AV1 in hardware and you have to clock symbols through, if each symbol has more information in it, you can actually handle higher bit rates with the same frequency hardware. So that was really important for the hardware story. We also have this Chroma from Luma intro predictor, which is another thing that came from DALL-E. This is a really fascinating technique. The idea with most intro predictors is you'll take your block and that you're currently looking at, and you'll look around it and you'll sort of pick a direction, sort of push whatever content across, was on the left or top of that block across the block, and use that as your predictor. And so this does really well for straight edges, like the branch here in this picture, or the border of your window when you're doing screen content. It doesn't do really well for curved images, or like the chrome on the window border. And so what this Chroma from Luma intro predictor does is it basically just takes the Luma content that you decoded, which is the grayscale version of the block, and just multiplies it by a number, and that becomes the chroma component. And so this does a really great job for doing prediction of curved regions and other areas where you can't predict very well. Like in particular fast motion, right? So you're already going to decode the Luma, and now you can get the chroma, get a chroma, like an accurate chroma predictor just from the Luma. And then the final one is this constrained directional enhancement filter. And so this is a combination of 2 experiments in AV1. The first being this DALL-E deringing filter, which was a directional filter we created in DALL-E to take care of the ringing artifacts I talked about earlier. DALL-E had a lap transform, which was a sort of novel transform that had a much larger spatial extent, and that meant that when you did heavy quantization, you ended up producing these ringing artifacts that kind of like extended much farther than other codecs. And so we created this directional deringing filter as a way to minimize the visual artifacts that showed up. It turns out that it works really well for other codecs. So we presented that to the codec working group, and at the same time, Thor had this constrained low-pass filter, which was a low-complexity in-loop filter that did sort of something similar to what the deringing filter did. It tried to find pixels that were not matching the local environment and then just clamp them so that they match the local environment. And we found a way, just like with Opus where we collaborated, we found a way to merge these two and create something that actually performed better than either one individually. So we would run a test with the deringing filter, a test with the CLPF, and then if you ran CDEF, it would be better than each one of them individually and each one of them in sequence. So it actually was a great win. All right. The next thing I want to talk about is the results. So how well are we doing? I told you at the beginning that our goal was to hit a 30% bitrate target, and our numbers showed that we were getting there, but it's always better to look at what a third party says. So here's a study from Moscow State University that was published in January. They took a version of the codec from June of last year, and then they compared it to two different codecs. They compared it to actually 4 different codecs. They compared it to X264, to 265, to VP9, and then AV1. And they found that if you look on the right side of this graph, the 264 class of codecs, that's what the 100% is. They all show some compression gains, and there's this sort of significant drop off as you move from 264 to 265. And then again, if you were to follow that down, VP9 actually is better than 265 at all different encoding options, with the exception of these placebo modes, which are these sort of modes you never use that try sort of an exhaustive search. So VP9 actually is a little bit better than 265 for most cases, except for this sort of video on demand case. And then again, you see this sort of drop off as we go and look at AV1, which is nice because it sort of proves that this approach we're taking of sort of bringing together all this technology is in fact kind of a generational improvement over the current state of the art. And the results show about 30%. Just to kind of give you an idea for what the history of development looked like, because this is something you don't typically get a picture for. You sort of see at the end, like, how well did we do as a codec? Well, over time, this graph here shows over time, how our compression performance improved given a baseline of AV1 back in July of 2016. And so you can sort of see, as we're adding more and more things, we're getting better and better compression. And when we get down, towards the end of last year, we were getting close to 30%, and we thought, we're getting near a place where we can finalize this. The big spike you're seeing there is because we had a regression, so this happens, but we ended up fixing that. If you look at this graph, this shows over the exact same time period what the complexity is, meaning the cost of encoding video over time. And so here we're actually measuring whereas as in the previous graph, like lower was better, here lower is worse. This is a graph where the y-axis is frames per minute. And so you can see we started out at some kind of almost real-time frames per minute. Excuse me, not even real time. So we had a, I think that should be frames per second. We had a somewhat real-time encoder, and as we went forward, it ended up becoming much slower. That's a logarithmic scale. So those compression gains came from basically adding additional coding tools that had additional modes of operation, and our reference encoder is doing sort of this exhaustive search over those modes. And we expect that, now that we've gotten closer to finalizing the bitstream, we'll now go back and revisit those decisions, come up with some heuristics or other ways to kind of cull that space down, that search space down, and get back some of the complexity cost. The other thing I want to talk about is the sort of what things look like for the current licensing environment. So a lot of the interest in AV1 is currently coming because the licensing environment around HEVC is somewhat difficult, to put it kindly. In June, Leonardo Cerliglione, the co-founder and chair of MPEG, wrote this blog post. This is where this image came from. That sort of lamented the current state of the art and said, well, hey, this MPEG business model is totally broken. And the idea, the business model I was talking about is this idea where you would take the best technology from participating companies, regardless of the intellectual property rights, and use that to form a standard that, is maybe best in class for all the use cases you care about. And then later, after you publish that standard, go back and figure out, how you can possibly create a licensing model around it. And so what ends up happening is that you're kind of guaranteed to create something that has this patent encumbered nature to it, just because people have been taking part in this process for 30 years. They've learned how to game it. They've learned how to, craft their patents so that they read on very specific parts of very specific pieces in the codec. And then over the same time, we've got these non-practicing entities that have become more aggressive, right? So in the past, maybe it was okay if everybody included their intellectual property, because at the end of the day, they're all going to want to figure out how to license it. So they're going to come up with some fair and reasonable licensing terms. now you've got companies that have no plan to ship a codec, right? So they're literally showing up trying to sneak their, I won't use the word sneak, trying to get their technology in because they know that once it becomes a standard, you'll be forced to license it. And so that basically means that your standard now is kind of vulnerable to patent holdup, right? And this is where you've got companies that have technology in the standard, and it may be very minor technology, which on its own, if you were to value the intellectual property, may not be worth a whole lot, but because you're required to license it, it now has a lot more value. And the result is that companies that contributed to making HEVC, some of them can't even afford to license it and use it. So this ends up being kind of a big problem, and has been part of the reason why there's such interest in AV1. To kind of get more specific, and I won't go into all the details here. If you're interested, you can go to the Wikipedia page and read all about the licensing terms. But I want to bring your attention to a couple of things. So the first is that the licensing caps for HEVC are much higher than they were for AVC. So currently, I think for AVC, the cap is around 9 million or 10 million a year for the annual royalty cap. If you look at it, if you look at the same category for HEVC, it's closer to 60 million. It used to be higher, closer to 100 million. That's just for the royalty cap. If you're shipping units like hardware units that have an implementation in the hardware, there's a different set of licensing schemes. If you're shipping content, like if you're a content producer and you've got titles that you're encoding, there's a per title licensing that you have to keep track of. And so the first thing to kind of point out is that this is much higher this generation. And the other thing to note is that there are, like, even though we have these numbers and you can kind of estimate what it costs to license HEVC, there's still members, if you look at this picture, there's still members who aren't in any patent pool, right? Who have technology that we know is in HEVC, but they haven't given out any licensing terms. And so if you were to try to ship HEVC today, you maybe could license it from some members, but you have no guarantee that you could license it from all the members. So if you were to, you go deploy, and then maybe those members later show up and say, we need this much money, and you have some uncertainty. So the market has been slow to adopt HEVC due to these concerns. So what's next for AV1? We're working on a bitstream freeze. That's sort of imminent. We announced the release of AV1, and we have a draft spec up. We're doing an engineering review, and we expect that process to be done shortly. What this means is that the streams that are encoded will always be decodable. It doesn't mean that we're done getting compression gains, because now that we have a finalized bitstream, we can go through and develop different algorithms and heuristics at the encoder level that take advantage of all these new techniques. And we kind of expect to see additional gains coming from AV1, even beyond the ones that we published, as people find new ways to encode video with it. We're looking for adoption from content creators and desktop browsers. We're trying to build, I think there's a project at Mozilla to build a production quality encoder that handles both the video on demand and the real-time streaming case. We're talking about maybe going back to the IETF and looking at to see if we can get AV1 into the RTP streams and add it to maybe WebRTC. And then there's a bunch of vendors who are working on hardware support, which you'll see in the next year or so. We'll turn over to Michael now.
All right, thanks, Nathan. So I wanted to give you sort of a brief introduction to how we do development on AV1. These are tools that we've built within Mozilla to help us at every step of the way figure out exactly how a change to the codec affects its performance. Oh, actually, wait, give me 1 second, I have to. Nathan, can you unshare your screen? Is this working? Okay. All right, so this is a tool that this is called AubreyCompress. It's a website you can go to, and you can keep track of and look at the progress we've made over time. And what you'll see here is on the left-hand side, we have a list of runs. These are commits to our repository with changes. So anytime a change is being made to the codec, you're able to go in and investigate its performance compared to other changes you've made to the codec. This is critically important because you know, when you develop codecs, you were making small changes, but these changes, you know, different kinds of video content behaves differently based off of the change you've made. So it's really important to really investigate and understand exactly what's going on. So let me give you a brief demo of this tool. So here what I've done is I've selected 2 runs. On the left-hand side, you'll notice that 2 runs are selected. These are 2 different Git commits. And the first thing we have here is a plot of its performance. So on the x-axis, you have you have the bit rate. On the y-axis, you have the quality. So what this is saying is that at different bit rates, so comparing, you know, the red line versus the blue line, at different bit rates, you have different qualities. So when we talk about how well a codec is doing, we're really talking about at a certain bit rate, how much better in quality is it compared to another version of the codec. So at any point in the way, you can look at the height difference between these 2 curves to sort of identify how much better this is one version of the codec as opposed to another. Now, one of the difficulties when dealing with codecs is it's hard to determine which one actually looks better. So to do that, we have a variety of metrics. So we have about 8 or 9 metrics that we measure and monitor at all times to see if the changes we're making actually result in an improvement. We'll also aggregate these on different kinds of content. So it'll be like 1080p content, 1080p screen content, smaller content like 360p, 720, so forth. And then for a large variety of test cases, we look at and we see how well we're doing. So this is, in this particular example, one of the codecs is in fact like 33% better. Negative here actually means is better. For some content, we're actually regressing, right? So this is sort of unavoidable in general because building a codec that works better across the board is pretty difficult. But one of the interesting things that we've built is the ability to compare side by side how 2 codecs interact and behave. So if you go to the site and you select 2 jobs, one of the neat things you can do is you can go down here. So let's pick StarCraft as one that I usually like to look at. So what we're doing here is we want to look at what the video quality looks like between 2 different versions of the codec at a certain quality setting. So if we click on 63 here, we're loading up this tool called the AOM Bitstream Analyzer. And what this allows you to do is actually look at 2 different builds of the codec, and you can inspect exactly what is happening any step of the way. Now, the really interesting thing about this is it's actually running the codec inside the browser using WebAssembly. So anytime you submit a commit to the GitHub repository, we take that, we build it to WebAssembly, and we store it on the server somewhere. And when you use this tool, you pick that particular build of the codec. And then we're able to decode live in the browser and let you explore and understand what's going on. We've also added some instrumentation to pull some data out of the codec. So this is the tool that lets you visualize that and explore it. So here's a particular frame of the codec, and you can actually toggle between, by clicking 1 and 2, you can actually look at 2 different variants. Now, you'll probably notice, well, it might be difficult because this is streaming live, so there's another codec involved here. But you may notice that there's a quality difference between these 2 things. So we'd like to understand why that is the case. So as developers of this codec, we want to dig in deeper and understand what's going on. So you can sort of highlight and focus on any one area, and you can toggle between the 2 different codecs, and you notice there's a quality difference there, and we want to understand why. To do this, we have an ability to toggle a variety of visualization options. So for instance, one that's really popular is the split grid. What a codec typically does is it tries to partition a video frame into a lot of little tiny boxes, effectively, of different widths and heights. And what the encoder does is it tries all sorts of partitioning possibilities and to determine which one effectively will end up working best. So by visualizing this, you can kind of see what the codec is doing. So you can now toggle between the 2 different codecs. This is codec 1, version 1 of the codec, version 2 of the codec. You can also step through multiple frames. So this is the first frame of the codec, first frame of this video, but then we can toggle and go to the next frame. You notice that things are significantly different. Well, the reason for this is that the first frame of the video the first frame of the video was cannot be predicted from the previous frame because it's obviously the first frame, but the second frame can be predicted from the first frame. So a lot less information needs to be transmitted to encode the second frame of the video. You can actually take a look at it by clicking on the histogram view here. And this plots, what kinds of information is encoded inside of a frame any step of the way. Now, here, well, let's see. You can actually, let's decode multiple frames, so we have more things to look at here. But what you'll notice is that like the first frame is there's a lot more information transmitted in the first frame as opposed to subsequent frames, quite significantly. It's a little hard to see, but at the bottom here, you can tell how much data is how many bits are being sent for subsequent frames. You can also take a look at, what kinds of information is encoded in each individual frame. And this is a histogram of the kinds of symbols and components that we transmit with every single frame. So you can kind of step through, but you can also look and compare it to a different version of the same codec, a different revision, and you can try and understand how they differ. Excuse me. Another interesting visualization is looking at and you can kind of go through this at your own pace. It's quite fascinating. So I have another one loaded here. This is another video. So again, you can look at the histogram view of it. This one uses quite a few more bits, but still a lot fewer than the first frame. But one of the interesting things to look at is one of the layers is called motion vectors. So the first frame of the video, there's no motion compensation, no motion prediction. But looking at subsequent frames, you will notice that there are these things called motion vectors. And what motion vectors effectively do is, say this, let's take a look at this. You can highlight a particular block. So what this is saying is that the contents of this block in this particular frame, second frame of the video, can be predicted based off the contents of the same sort of area, but in the previous frame. So when this frame is encoded, we're able to predict it from the previous frame. And the length of these vectors here, which are drawn in red and blue, indicate how the data can be pulled in from nearby frames to create this frame. You'll notice, you can actually turn off the image. And you'll notice that you can play it back. It's maybe a little difficult to see through video, but the areas of the frame that have a lot of motion end up having larger motion vectors. You can also go in and every step of the way understand exactly what is being encoded in each frame of video. So you can go in here and you can understand, you would have to have deep expertise and understand what the codec is doing, but you can get a sense of how many bits are spent to encode this particular block, right? So when we compare two different videos, two different versions of the codec on a particular video frame, we can see if we've regressed or we've improved things. You can also get aggregate information on the overall frame. And lastly, there's also the ability to I think it's not integrated in this case, but oftentimes when we're looking at video codecs, we can look at the numbers and the objective metrics, right? But sometimes we need subjective results. So we have an ability to create a voting or to be able to do a survey. So we'll take one video encoded with two different versions of the codec, and we'll create a voting or survey type of functionality. And we can send that link out to people, and the people can go through and vote on which they prefer more. Then we can use that data to then, sometimes break ties between two different features that we'd like to add to the codec. Okay, so going back to the slides, see if there's anything else to add. Although this tool is this is just a web page, effectively. If you'd like to run it locally, you can also do that. So we've packaged it as an Electron application that you can run locally, so you don't have to be connected to the internet to be able to use it. But I think that's all. I think that's all I need to say. I can open it up to questions. So Nathan, do you want to pop back on video?
Okay.
Sure thing.
let's see.
Wow.
Manel, and there I am. Here we go. I think we're all back in room. Flocky and Gabriel had many questions on the Etherpad. If either of you would like to pop into the room, show your faces, ask the questions yourself, welcome to do that.
I think we have Gabriel here.
Okay. There he is.
Yeah. Hi, can you see me?
Yeah.
Yeah, cool. Yeah, I had a couple of questions. The first one is that this codec AV1 is going to be available as a source of my video tag. So can I put it as a source? Or only through media extension?
So, I mean, that's generally sort of integration work on the web stack. So we're not like intimately familiar with how it's plugged in. But yeah, I mean, eventually you will be able to just get another codec that's supported by the video tag.
Yeah, okay. Okay, next question. How is it going to change the current WebRTC implementation, and what it will bring to the table? If you have any opinion on that.
So in terms of, once the encoder, encoder and the decoder are fast enough, right? Effectively what this will mean is you have higher quality. I mean, when it comes to codecs, you have, like you can look at, for the same amount of bandwidth, you can get higher quality video, right? Or for the same quality video, you spend fewer bits, right? So fewer interruptions in your streaming conversations and things like that.
I think the other thing to consider is just the impact of having sort of a high performance royalty free codec, right? So that we've already had better codecs for video compression, but we haven't seen a lot of adoption just because of the licensing space, right? So the fact that AV1, is royalty free because we've got people actively trying to make it royalty free, and we've got the IP from these 33 companies, and those 33 companies are going to be shipping it, means there's a strong likelihood that people will actually pick this up.
Yeah, I see. So I know maybe it's like a early question, but what if you had to build an app where you want to stream HV with HV1? How would you do that? Would you do it through WebSockets, or would you use WebRTC? How would you make a stream to the browser?
Yeah, I think Michael's point earlier about us not being involved in the integration side is a good point, but I will tell you that there is work to add it to WebRTC, right? Like I think once the standard is finalized, we're going to bring this to the IETF and get it included in the RTP payload, right? As a formal codec. So you'll see a variety of different ways of playing it, but.
So maybe something to add is that if you look at a codec, right? Generally what people consider codecs are, oftentimes they talk about container formats, right? And like MP4, for instance, right? That's not a codec, it's more of a container format. So the AV1 code base, a lot of it is sort of a derivative of the VP9 code base. So anytime you look at VP9 and how it's being used in the wild, whether to watch YouTube videos or stream it, AV1 more or less will follow the same sort of path. So there will be some work necessary to package AV1 bitstreams into existing container format and channels.
Yeah, thank you.
So let's see, am I audible? I'm not sure if am I muted.
Yeah,
you can hear me? Can you hear me?
Yeah, we can.
Oh,
yeah.
Okay, I was just going to make a comment. I think this is really interesting because Michael and Nathan are from Mozilla Research. They're really they're working at a much different layer of the stack than we web developers are usually thinking about. And so it's just interesting to see like there's a little bit of a gap in the stack there between the questions that you're asking as a front end guy and the work that they're doing. But I'm learning from all this too. If you guys could unshare the screen, then we'll have more FaceTime on the.
We did, actually.
Did that happen? Okay.
I'm not sure why it's still.
Okay. All right. No worries. That request
Okay,
came
I
in.
will.
Yeah. Go ahead. Let's carry on. Thank you.
Yeah, we still have some couple of questions, so I will take. I'm gonna share the first one from Flaky. So he's asking what will happen to the Bitstream Analyzer, as we know that it's the Bitstream freeze is happening now. So is there still a use to the tool or not?
So development work, so once the bitstream is finalized, right, that's like saying that HTML spec is finalized, right? But it doesn't, it can be used in many different ways. So work will still continue on improving the performance of the codec. And to do that, you need to be able to inspect what the bitstream looks like. So the choices that an encoder makes, you'd like to be able to visualize it. So it's still useful as a tool to help codec engineers improve the performance of the encoder. Secondly, it's also useful for content authors that, oftentimes when you use a codec, you're prompted with, 30 different knobs you can tweak, right? And you'd like to be able to understand how those knobs ultimately affect the video that have been encoded. So it may also be useful for content creators to understand and see how the changes or the options they've set in the encoder affect the video. One of the nice things is once the codec is freeze, then we can actually, like the Bitstream Analyzer will work on all videos, all AV1 videos, as opposed to being tied to any one particular revision of AV1.
Okay. I hope that answered the question to Flaky. So yeah, I got another one. So he's saying encoding AV1 is still very costly, but can we expect decoding speed to improve to a point where polyfiling an AVA1 decoder could become viable, like via WASM, for example? Or do we expect browsers will implement fast enough that it would not be a pressing need?
Yeah, so currently actually in Nightly we already have libaom integrated, so you can actually decode a certain commit of AV1 right now, done natively, using not using a shim or any kind of polyfill. And in fact, we've done demos with Bitmovin where they've done real-time decoding of 1080p in the browser. So decoding decoding performance is not the same as encoding performance by any means. The decoder actually has tracked very well. We haven't had too many regressions, and again, that's due to the fact that the encoder has sort of like expanded the search space, and the decoder just has to decode the one thing that you signaled. So we still believe that decoding actually should be mostly fine right now. We've got some work ongoing to improve it, but I think sort of starting from the bitstream freeze, you should be able to decode in the browser.
Cool.
Thank you. There's another question from Flaky also. So he's saying, can you tell us a bit more about the challenges and interesting aspects of working with such a diverse cross-company team on the same code base?
Yeah, it's similar to other standards work where you're kind of presenting things and you've got to convince a large consortium of people who have very different and competing interests that your approach is better. So I think it's been maybe not as bad as some of the very bad sort of standards work I've done, but it's definitely been challenging, right? So as I presented, like we've had a lot of collaborations. There's a lot of compromises we've made. So the CDEF filter had gone through many iterations where we took feedback from NVIDIA, we took feedback from other hardware vendors and incorporated that, and eventually came up with some design that was suitable for our needs, plus the hardware vendors' needs and things like that. I can say that compared to previous efforts to make a royalty-free video standard, having all these companies buy in and look at the work while we're developing it, even though it may be more tedious and maybe we have to jump through hoops we didn't want to jump through and care about use cases we didn't want to care about, we actually now have a better product because we know that people will ship it. And so it's worth the effort to do that.
Yeah, one of the interesting things working with hardware companies is that, unlike other software products or projects, you really have to be careful about, your design to make sure that it's feasible in hardware, right? Like some piece of code that you write ultimately has to be implemented in silicon. And it needs to be possible to do that. So getting the feedback from the hardware companies while we're designing the software is also really important. Now, because hardware is likely to appear sometime in the future, to get adoption of the codec, we also need to make sure that the software performance is good enough, right, to sort of tie us over until we have, devices out there and televisions that can decode. So it's an interesting compromise. It's certainly a challenge, but it's fun.
Yeah, it sounds like fun. So we have another question from Vicky. So she's asking, has AV1 been deployed to any chipsets for hardware encoding? If no, what's the adoption process?
Right. So, I mean, we only made the announcement about the release of AV1 on March 28th, and there's still some normative changes to the bitstream. So obviously, like, there's no hardware that is shipping with AV1 today. We do know that there are vendors who are working to get products out. Probably you'll see them in 2019. You'll see a lot more a little later than that. And in terms of adoption, the software story is really where it's at. Like Michael said, we've been working hard to make sure that the techniques that we add for AV1, even though they will implement well in hardware, like they'll also implement in software. And so several people have looked at ways to do parallel encoding where you chunk a video up into small sections. We've got tiles, so you can actually have sort of spatial and temporal parallelism in terms of encoding. And for companies like Netflix who have a smaller category of content than say YouTube, they can actually invest in the cloud resources to do that type of encoding. So there's still a possibility that you could see early adoption from companies like Netflix and use cases similar to that, like video conferencing, right, where it's totally ephemeral. You do it once, and there's no, it's not super high quality. That you could see places where that might be adopted early using software solutions.
Okay. We have got another question also from Marriott. So he's saying that he heard that compressing text in images greatly reduce the images qualities. Is there the same problem with video? How does EVA1 approach this problem if it exists already?
Yeah, so I mentioned it a little earlier, like there are specific tools we've added to AV1 to handle coding screen content. Particularly, I mean, this is the text issue, and this is really important for screen sharing, for video conferencing, for those use cases. One of the ones that's been really effective is this idea of palette mode. So it's, you create an index of colors, and then you code the index, and now when you do your compression, what you come back with no longer has these like crazy ringings on them because it was encoded using this sort of transform mode. It's encoded with this sort of palette, and that ends up doing a good job of matching the original screen image. And then, like I said earlier, there's these extra filters we have, and in particular that the directional, the constraint, the CDEF, the constraint directional enhancement filter, does a really good job of smoothing out these edges on the screen content where you have sort of garbage added by your text ringing way out. And this is similar to how other modern video codecs try to approach the problem as well.
Cool. Can you hear me? I'm sorry. I'm really bad with mute buttons. So there's one more question that came onto the Etherpad from Andy. He would like to know, how long do you think before CDNs like Akamai are offering delivery of AV1 bitstreams? Are those conversations starting to happen? Or
yeah, so well, I guess we'll learn more about that. We're going to be at NAV next week talking about the launch of AV1, and there's a bunch of content providers there. I think a lot of that's predicated on seeing a deployment of software decoders, right? So if all the browsers ship this thing right away and there's a performance improvement by doing this transcoding to AV1, I guarantee that CDNs will do this because it will save them money, right? That's the name of the game, and the fact that it's royalty free means it's easy to do. I think you might see varying levels of adoption based on the content. So things that you could encode once and share over and over again, I expect to see encoded maybe first, just because you can do the investment up front, and maybe that will change over time to shorter lived things.
Cool, right. So NAB, for folks on the call, is the National Association of Broadcasters. I think it's a great big, like the CES of TV production and entertainment production. So that's happening soon. I'm going to do a last call for questions in the room. Gabriel, anything else on your mind, or anyone else? Thanks everyone for joining. I left some links to the Are We Compressed tool in the Etherpad. I'm afraid we didn't do a great job taking notes, but there will be the recording. It will be captioned, and we'll be sharing that. And I just wanted to thank Michael and Nathan for taking the time and talking about this really exciting project, which will also save, I think it's fair, I think hundreds of thousands, maybe more. It will save tons of money for Mozilla, which means we will be able to do other things that we all care about and that Mozillians care about. So last call for comments, announcements, questions. If not, expect this video. Okay. This video will be transcoded. I'll drop the link into the channels a little later today, tomorrow, depending on your time zone. And thank you again. Good luck, guys, in Vegas, and see you next time. All right, everybody.
Thank you. Bye.
Happy trails. Keep on rocking the free web, and see you soon. Bye.